Hello, Math 213, 221. Here with our another lecture, Antiderivatives. And before we get to antiderivatives, I do want to take about 15 or 20 minutes and talk about how we connect what we talked about last time to what we're doing today. Some of this is not in the book, so there's not going to be any homework or test questions on this, but I do think it's important that you see the logic of how this is built up. Because if you understand the logic better, you will better be able to do this. So first of all, with integrals, something you'll be able to do next week is if you have a complicated area like this, if you can fit functions to the boundary, you'll be able to figure out this area. Something you'll be able to do next week with integrals. Can figure out very complicated areas well beyond what geometry could do. And not cutting on geometry, though, we couldn't get here without geometry, but one of the powers of integrals. But let's remember where we were at from last time is we have some function, and we're going to pick endpoints. I'm going to choose a equals 0 for these problems, just to make the math slightly simpler with a 0 there. And I'm going to say b, our ending position, is x, because that'll allow us to take this black bar and move it left or right. And the question was, well, what is the area between the curve, the x-axis, and these 2 points that we give? And we talked about a scheme of filling in with rectangles. Now I am drawing out right rectangles here to fill in this region. As a quick note, there is a right rectangle right at the beginning here, but because the height of the function is 0, means the height of the first rectangle is also 0. But there is a rectangle in the first position, and this was our approximation. We're going to get this area of the curve with all these rectangles. And recall, these rectangles all had the same thickness of delta x. These rectangles are at a position xi, which is dependent upon if you did left, right, or midpoint. The height of these rectangles is always given by the function output, and that the area of these individual rectangles is simply length times width. So that in this case is the height of the function times delta x. And what we did then is we came up with an expression for that we took all these areas and we summed them together with this summation symbol, n being the number of rectangles. And what we're going to do is we're going to let these rectangles get smaller and smaller and smaller in thickness so that they become infinitesimally thick. We're going to let them get forever smaller, which allows us to put infinitely many in there. And as smaller and smaller these rectangles get, the closer and closer they'll get to the actual area under the curve. And then once we take the limit will tell us the ending process of all of these summations, which will be then the exact area under the curve. But before we get there, really quick, also recall that delta x was b minus a over n. Before we get there, though, I had to talk about a quick property here. Paste this over. And it comes from this summation. So I'm just going to take this summation symbol for 1 to 4. And if we write the whole thing out, so we'll have our x1, x2, x3, x4. This is what the summation symbol means. And recall I pointed out that there's a delta x in each of these, and that's the greatest common factor. And because of that, we're allowed then to factor that out. And so we can factor out a delta x here. And what I'm going to do this time, actually, is I'm going to stick the delta x in front. And it's multiplication, so we can stick it wherever we want there. And notice that inside the square brackets here, this is another summation. Because here's our indices, 1, 2, 3, and 4. And that means then that what's inside here, we can actually write as another summation. And we're doing that from 1 to 4. And we can replace then all of this with that summation symbol. And we don't need the parentheses anymore. And now notice this expression we have. This delta x, which was inside the summation, we were able to pull outside the summation. And this is a property with summations. If you have a constant factor, you can pull it out of the summation. So delta x is not dependent upon I, and that allows us to pull it outside the summation. And I'm going to need that property going forward to show you this stuff. So this is also something that happens with the limit, or if you have a constant, you can pull it outside the limit. Same with the derivative, and that will also be true with integrating. So let's take, actually, before we do a simple example, what we're going to want to do is take our expression here and our delta x, and we want to start combining all this stuff together. So first of all, I'm going to take this delta x and pull it outside the summation using our property here. And we know also that delta x is b minus a over n. So I'm just going to plug that in. I'm also going to say for all these problems here that a equals 0, because it makes this a slightly simpler to deal with right there. We're going to say a equals 0, and we don't need our delta x here anymore. Now also recall that we do have to choose what type of rectangles we're going to squeeze in here. And it turns out it's slightly simpler to choose left rectangles. So I'm going to choose the expression for left rectangles for our x sub I positions. A is 0 for these problems. We'll get rid of that. And delta x is b over n. So here's our expression for where all the rectangles are located at. And we're going to take this and plug it back in to this, our area formula here. So instead of xi, we're going to have I times b over n. And now we don't need the x sub I expression anymore. Here is our then super awesome area formula that will get us all our approximations, all in one. This is still algebra though, and what we're going to do is take then the limit of both sides so we can bring this into the realm of calculus. So we're going to take our expression and take the limit of both sides. Now the limit of a constant is always that constant. So left side is easy enough. That's just our a value. And the limit on the right is where the fun is. So here is our algebra expression. This is our estimation. But once we put the limit on here, this is now our exact answer. So this is the one that we're going to be using now. And let's do this for something you already know the answer to, a rectangle. So here's our horizontal function from 0 to 8. So this is 8 times 3, so this area is 24, something we can already get from geometry. How in the world can we get that from then this expression here? So first off, I do want to do this for all constant functions. So I'm going to use f of x equals c. In this case, c equals 3 to get the picture that I have drawn here. But I'm going to choose all horizontal functions. So what I'm saying here is that this function is going to be c. So the function we're choosing is just a horizontal function, c, and then you can choose any number you want for c. The graph on the right, I chose 3. So we're going to take this and plug it into our area formula. So all this function here is c. And c is a constant, and so we can pull it outside of the summation, which means all that's left in the summation is 1. So what we need to figure out then is what is this sum? if we sum 1 n times, well, that just means 1 plus 1 plus 1. We're doing it n times. And if you sum n ones, you get n. And so we can replace that summation then with n. This thing will always be n. Now notice these n's do cancel. And so we're just left with a b here. And now the limit, since there's no n left, the limit of a constant is always that constant. And so our final answer is c times b. And if you look to the right, c is 3, b is 8, and there's our 24 for the area under the curve between 0 and 8. Now I want to let b be x so that we can move this green bar here left and right. I'm going to make that a variable. So I'm going to change this a equals cb here. And let's just change this b to an x. And let's give this a function name instead of a. And notice that if we take the derivative of both sides, so the derivative of c x with respect to x, well, that derivative is just c. And notice c is the original function that we started with. So that's pretty cool. We started here with the limit of this summation. We started with summing infinitely many rectangles, and we ended up getting a relationship to the derivative. So let's check out another one that you know the answer to. And again, let's start with our general expression for the area. Let's do another one. Right rectangle. Hopefully you know this area because it's half of a square. So the square is a 20 by 20, so that's 400 divided by 2. So we have 200 for this green area. And again, I'm going to use a general expression here for a linear function, which is m times x. So the slope is m. The graph I have drawn has m equals 1. So you're seeing this function here. And that is our function then that we're going to define for our area expression. Is we're saying this function is equal to m times x. But remember, x is the position of all the rectangles, and that position is given by I times b over n. So our function here is mi b over n. And we're going to replace that into our summation. So this would be mi times b over n. Also recall, if something is constant, we can pull it outside the summation. So m right here, that's not dependent upon I, so we can pull that outside. B over n is also not dependent upon I, and we can pull that outside. And there is our expression. So now we have another summation here. In this case, we have the sum of I, and this sum was already figured out about 400 years ago. I think Gauss, supposedly as a 10-year-old, figured this out. So we'll just take advantage of his genius. The sum of I n times is 1/2 n times n plus 1, where n then is our number of rectangles. So we're going to take that expression that someone's already figured out for us for the sum of I. So this is 1/2 times n plus 1. So we got rid of the sum by using something that's already been figured out, and now we want to do this limit. But before that, let's clean this up a little bit. So for instance, we have an n that can divide out in one of these positions. B times b would get us a b squared. And what we're going to do is we're going to take the n in the denominator and distribute that into the parentheses. So we're going to get rid of this n here and put it into the parentheses. So n divided by n is 1, and 1 divided by n is 1 over n. And just cleaning this up a little bit, so this 2 we can stick under here. Maybe this m, stick there. And here's our limit we're taking. Now the same thing with the limit. If something is constant, like mb squared over 2, we can pull that outside the limit. And then the limit distributes, so we can take the limit and distribute it to each of the terms. The limit of a constant is always that constant, so the limit of 1 is 1. And 1 over n, 1 divided by a larger and larger number, that's going to 0. So this limit here is 0, and then 1 plus 0 is 1. So our final answer, our exact answer, is mb squared over 2, which should be the answer you already expected, 200. So how do we know that? Well, if we look at our information, m is 1, so we have b squared over 2, which is half the area of a rectangle. So we got the answer you already knew from this process. Oh, also notice, if we let b go to x, so let's write this again as b, but we'll replace that with x. Replace this with some function notation. And again, notice that if we take the derivative of both sides, so the derivative of x squared is 2x. So the derivative of x squared is 2x. These 2's will cancel, so you're just left then with mx. And again, notice mx is the original function that we started with. Let's do one more example. Since I haven't done anything with curvature yet, let's check out good old x squared. And we're going to go from 0 to some b value that we'll call x. So we start with our general expression for the area. Now in this case, our function, so it's x squared, so this is x, and that means then that we're going to square all of this. So here's our function expression that will stick into the summation here. So instead of this being function notation, this will actually all be parentheses squared. And then once we have that, we'll take things out that are constant. So notice this is b squared, n squared. This is not dependent upon I, so we can actually pull all of that out of there. And so we're just left then with I squared here. And then this summation is the one we would need to figure out. Somebody has already figured out what this answer is. And I don't know it offhand. Just pulling that up. So the summation of I squared from 1 to n already been figured out for us. It's this expression here. So we're just going to take that result that someone's already figured out for us and just plug it in. So this summation is a 1 over 6 times n plus 1, 2n plus 1. So here's the limit we need to figure out. And we need to clean it up a little bit. So first of all, in the numerator here, we have b times b squared, which is b cubed. And that's constant. Remember, if it's constant, we can pull it outside the limit. So we can pull a b cubed out of the limit. This 1/6 is also constant, so we can pull that out of the limit. And so now we have an n cubed down here. And this n and this n cubed, so that'll cancel to give us an n squared. And then lastly, we will want to distribute these parentheses here. So n times 2n is 2n squared. And then we have n times 1, which is n, 1 times 2n, which is 2n, to give us 3n, and then 1 times 1 to give us 1. So just distributing that out, the FOIL method there. And then we're going to divide everything. We're going to take this 1 over n squared, stick it into the parentheses, which means we're going to divide everything in the parentheses by n squared. So n squared divided by n squared is 1. N divided by n squared will be 1 over n. And then 1 divided by n squared is 1 over n squared. And now the limit distributes, so we can distribute the limit to all this stuff into parentheses. And the limit of a constant is a constant, so the limit of 2 is 2. And these other two terms, so 3 divided by something going towards infinity, means this is going to 0. And same with the other term. 1 divided by infinity is something going to 0. So 2 plus all those zeros is 2. And then this 2 and a 6 have a common factor, so that gives us a third. And that is our final answer. This green area on the right is b cubed over 3. Now notice that b equals x, so that we can move that around. Let's say b equals x. We'll call this a function name. And again, notice, if we take the derivative of this expression, the derivative of x cubed, so that's 3x squared. And then these 3's cancel, and so we're just left with x squared. X squared, which is our starting function. So notice in all 3 of these examples, our answer, if we took the derivative of our answer, we get the original function back that we started with. So let me state that mathematically. Where we started, our main expression for the area. If we take the derivative of this expression, we get the function back. Now this is a lot of notation here that has been shortened over the years. And so we're going to get to what that shortened notation is. And to do that, I do have to change back into our delta x expression. So if you recall, this b over n is delta x. And this IBN, this was giving us the x positions. So I'm just changing back to this notation here. And this delta x, I'm going to stick back into the summation. So just rearranging it to look like this now again. Because the notation change here, because this is so much to deal with, is the notation change then is that this limit, as n goes to infinity, along with the summation sign, all of this gets expressed then by the integral symbol. And then we have our starting point on the bottom and the ending point on the top. So this limit and the summation symbol all gets replaced by this integral bar. Now the integral symbol does have this b on top and a on the bottom to indicate where you start and stop. And ultimately this symbol is called the definite integral. And I'm going to cheat a little bit here though at this point because of the topic today, which is antiderivatives. And what I mean by that is that we're not going to have any symbol on the top or bottom here. And without the a or b, this is then called an indefinite integral. And we'll talk more about what this means. But the point for this first section here is just antiderivatives. And this has to do with indefinite integrals. I'm going to take our expression here, and instead of the limit and the summation, instead of that, we're going to use the integral symbol. Something else that changes here, if you recall, I mentioned this one or two times in class, that the change from algebra to calculus, in algebra you have delta x. This is a finite quantity, can be small or large. But in calculus, this goes to an infinitesimal, which is then what we write as dx. And so since we're taking our expression and making it into calculus here, this delta x does go to dx. And we no longer need to increment the i's anymore, because now dx is an infinitesimal. And this is our expression. And then this is our integral. And this integral gives us the antiderivative. So this expression here in blue, this is what gives us then, this answer is called the antiderivative. So just to connect this back to what we're doing here, if I take our expression without the integral symbol yet, this is the antiderivative. So again, notice what the integral stretched out symbol s is replacing. It replaces the limit in the summation, and then delta x goes to d of x. So the goal of this homework is going to be solely to get these antiderivatives. And the antiderivatives is just doing the derivative backwards. Let me give an example of that. Let's say that this is simply x cubed in here. So the antiderivative is asking you what gives this derivative. So if we look at x cubed, well, we know the derivative subtracts 1, So doing the reverse of that means we add 1. So the exponent goes to 4. Now remember, if we take the derivative of x to the 4th, this 4 drops down, and we don't want that. And so we can divide that out with a 1/4. Now check that out. 1/4 x to the 4th. If we take this derivative, our derivative, the 4 drops down, they cancel, and we'll be left with x cubed. And this is the antiderivative. Now these are called indefinite integrals because when you take the derivative of a constant is 0, which means we could have a constant on this function because the derivative of a constant is 0, and so this will also get us back to our x cubed. So with indefinite integrals, we always have to put on this plus c because we don't know the definite answer. All we know is the answer is of this family of solutions, in this case of x to the 4th polynomials. And now you're in a position where you can always check, because your answer, if you take the derivative of your answer, you should always get the function that you started with. So if you're a person that does like memorizing formulas, I think it's, for myself at least, easier to remember that integrating is just the reverse of the derivative. But for polynomials, if you have x to the n, now instead of subtracting 1, when you integrate, you add 1, and then you always have to divide by that n plus 1. So this is actually the general formula. This is our integral pattern. Just like we had derivative patterns, well, here is our integral pattern. And that's the antiderivative. This expression, our answer here is the antiderivative. And if you take the derivative, you should always get back to where you started. So you can always check your work with integrals. Let's just write these patterns out here. So here is our power series. So we had a power series derivative. Well, here is our power series integral. What was another one we had? Another one we had was exponential functions. So a base raised to some value. And recall, the derivative of an exponential is always itself, and so reversing that process, well, integrating an exponential is always itself. Now recall, when you take the derivative, there's a natural log of b that pops out. That's from taking the derivative. When you integrate, however, remember it's the reverse of that. So now instead we have our log base in the denominator. And again, for indefinite integrals, we always have to have the plus c to indicate that there could be some constant there. And the other expression that we had is logarithm functions. Now recall, the derivative of a log is 1 over x. So that means integrating 1 over x will get us to our log function. Now also recall, when we took the derivative of log, we would get a 1 over x and then a 1 over natural log b. Well, in this case now, the natural log of b sits in front. Now I do want to quickly point out the special case when you have base e. So if this base is e, remember log e is 1, so this whole thing is away. And the integral of e is e, just like its derivative. And for logarithms, if we do have base e, so right here, so remember log e is 1, so we can actually get rid of all that. And also recall that log base e, that's written as ln. And so these are the two special cases then if you have log base e. These top tier expressions, though, those are our three patterns for the integrals, just like we had these three patterns for derivatives. Now for 221, of course, you do have all the trig patterns that add on to this then. So for 221, let's say you had the integral of sine x. Well, sine x comes from what derivative? Well, remember, cosine of x, the derivative of cosine is a minus sine. And so to get rid of that minus then, we just stick a minus there. So the integral of sine minus cosine. And what about the integral of cosine? Well, what derivative gets us cosine? Well, the derivative that gets us cosine is sine. And just to do a quick more here, since there's also the tangent function. Now the tangent actually comes from secant squared. So the integral of secant squared, what derivative gives secant squared? Well, that's tangent. Now the integral of tangent is usually a homework type of problem, and so I'm going to leave that for the 221 people. So two properties that are very useful with the integral. Something you're already familiar with, the derivative, as the constants do pull outside the integral, just like with the derivative. So say we have a constant and some function, and we can pull that constant outside the integral, just like we can with derivatives. Another useful property of that the integral has is that it also distributes. So let's say we have two functions here. Then the integral will distribute, just like the derivative does. So these two properties are going to be useful for the homework. And these are already things you're familiar with. The derivative constant will pull outside the integral, and the integral distributes. So let's check out some problems. Remember, the only goal here in this section actually is to practice getting antiderivatives. So here's our problem. First off, there's a constant, and we can pull that outside the integral. And recall another thing that's nice to do here is to write everything in the numerator. So x squared, if we bring this up to the numerator, remember that changes the sign of the exponent. So that'd be the x to the minus 2. And so we want to think then, well, what gives us a derivative of minus 2? So first off, we always have our 5, our constant, is sitting out there. That'll multiply whatever our final answer is. So we add 1 to the exponent now. So minus 2, we add 1, goes to minus 1. And then we always have to divide by that new exponent. And we always need to have our integration constant there for indefinite integrals. And then that's our answer. And this is something you can check. Take the derivative. So the derivative of a constant is 0. And the derivative of x to the minus 1, so the minus 1 drops down, makes the minus 5 a positive 5. And then the minus 1 goes to a minus 2 when we take the derivative. So you can always check these problems. So let's check out another one. So we want to integrate x squared minus 2x plus 1. So we want to find this antiderivative. We want to find what function gives this derivative. So again, the integral does distribute, which means we can do each of these individually. So x squared, what function has the derivative x squared? Well, that comes from x cubed. Now the derivative of x cubed is 3x squared. We don't want the 3. And so remember, we have to always divide by that new exponent. So the integral of x squared is x cubed divided by 3. Let's look at the second term. What function has a derivative 2x? Well, that's x squared. The derivative of x squared is 2x. And now what function has a derivative of 1? Well, that's just x. The derivative of x is 1. And then we finally have to tack on our integration constant, this c. Since we don't have our a or b, we don't have the limits, we don't know the area yet. What we do know is the function that will give that area. That's the antiderivative. Let's check out another one. Here's one where the book is trying to be a little cute with you. They got the integral of square root of x over 2 plus 2 over the square root of x. So recall that when you have this square root of x, a good thing you might want to do is to change this to its proper exponent. Remember, the square root means a half. We'll change that there. Change this one down here. So that might be something you want to do first. And also recall that we want these exponents to be in the numerator. So to get this into the numerator means the exponent will get a minus sign change on it. So putting that into the numerator would make it minus 1/2 then. Now the integral does distribute, so we can do each of these individually. So first off, we have our half here. Remember, a constant can pull outside the integral, just like with derivatives. So we're integrating x to the half. Now, what function has that derivative? Well, a half, remember, subtracting 1 from the derivative or adding 1 to a half will get us 3/2. So the derivative of x to the 3/2, we subtract the 1, this 3/2 goes to a half. And then also recall, we always want to divide by our exponent. So dividing by 3/2 actually means multiplying by 2/3. And again, you can see right here, the 3/2, when it drops down, it'll take out this 2/3 to get us a 1. And then we'll have our half. And then we'll have plus 2. And we want to know what function has the derivative of x to a half. Well, we'll add 1 to that exponent. So adding 1 to a half gets a positive half. And remember, we always want to divide by this new exponent. But division by a half is the same thing as multiplying by 2. So I can stick another 2 there. And then we always want our integration constant. Of course, we could clean this up a little bit. So like these 2's cancel here. And so this would just be 1/3. And then 2 times 2 is 4. And again, what's cool with integrating is you can always check your answer. Take the derivative of your answer, and that derivative should always get you back to the original function here. So let's try another one where the book is trying to be a little tricky with you. And we have this case here. So again, a good first step is to get rid of these square roots and write it with the proper exponent. So the square root of t is t to a half. And also recall that we can combine these exponents. So t times t to the half means we can add these exponents together. So it's 2 over 2 plus the half to get us 3 over 2. And again, this t over here we can write with its half exponent. That's a good first step, cleans it up a little bit. And then what we want to do here, I've mentioned this a few times with things, is we want to decompose this back into fractions. So we want to divide each of the numerator terms by t. So we can do that by doing something like this. We're going to have that first term divided by t, and then plus the second term divided by t. So that's breaking it into fractions. And once we do that, we can then simplify that. Since t cubed, t to the 3 halves, divided by t to the 1. So remember, we subtract these exponents now. So it's 3 halves minus 2 halves to get us a 1/2 for all of that. And over here, we have a half minus 1 to get us then a minus half for that simplification. And so this integral that was started here actually can simplify down to this. And now we can simply use the power derivative here to reverse this. So we know t, we add 1. So we know a half comes from a derivative that is 3 halves. And then we always divide by that new exponent. Now division by halves, division by half is the same thing as multiplying by the reciprocal, so that's 2/3. And let's look at the next term, t to a minus half. What derivative gets us a minus half? Well, that's a positive half. And again, we always have to divide by the reciprocal. And of course, division by the reciprocal, division by a half is the same thing as multiplying by 2. And then we finally have to add our integration constant, since we don't have a starting or ending point yet. All we know is the antiderivative. We know the function that will ultimately give us our answer. And again, this is always something you can check. So if you take this derivative, the 3/2 drops down, and that'll take out the 2/3 to get a 1, which is what we want because there's nothing in front of the t. And 3/2 will go to a 1/2. So indeed, the derivative of this is this. And likewise over here, we take the derivative here, the 1/2 drops down. 2 times a 1/2 is 1, so that's what we have right here, the 1. And then 1/2 minus 1 gets us this -1/2. So indeed, this has this as a derivative. And of course, the derivative of a constant is always 0. That's something that's kind of cool with integrating. You can always check your answers. So that'll wrap it up. And let me just say this in closing, that this picture here is the list of our derivative, our integral patterns. Now, I do encourage you to think of integrating as reversing the derivative. I think it's a little bit simpler than memorizing a whole new set of equations. But if you want to do that, here are the integral patterns then for the power series, the exponential, and the log. And then here's a few trig ones for the 221 class, and the 2 properties then of the integral. So we will talk more about all this area stuff. We'll talk about definite and indefinite integrals and what that all means further. The only point of this homework is to have you practice getting these antiderivatives. That's the only point. So we'll talk more about area and definite integrals in our next lecture.